Yes, we'll turn our gaze to a different kind of computational science application. Yulin Pan is from Naval Architecture and Marine Engineering, also part of the most recent cohort of Catalyst grants. Yulin's project is on real-time ocean wave forecasting by rapidly assimilating data on the fly and using GPU acceleration. Thanks, and I'll turn it over to you, Yulin. So I'll do the same as with the others, Yulin. I'll give you a heads up around 20 minutes into your talk, so you have.
Okay. Yeah.
Great. Yeah, thanks.
Can you see my screen?
We can see you. We can't yet see the slides. Okay. So if to the right of your screen, very right, you will see a sign with mountains. Okay, there you go. You found it. Yep.
Okay. Can you see it now?
Yes, we can see it. Go ahead.
Okay, great. Thank you very much, Krishna. This is Yulin Pan, and I'm an assistant professor in the Department of Naval Architecture and Marine Engineering. It is my great pleasure today to present my MACD project, Real-Time Phase Resolved Ocean Wave Forecast with Data Assimilation and enabled by GPU-accelerated computation. Together in this presentation is Guangyao Wang, who is a postdoc working full-time on the data assimilation problem, and Alex Rapsky, graduate student working part-time on the GPU computation. So why do we need this project? One of the major concerns in the marine engineering is a stochastic ocean environment, which imposes considerable threatening to the integrity of all the marine structures, be it an ocean platform, offshore wind turbines, a ship, or a fish farm. The survivability in the extreme sea states is an important consideration in the design of all these structures. And in the meanwhile, another concept that people consider is a wave prediction. If we can do the wave prediction pretty well, sufficiently well, then we will be able to operate these structures in a smart way according to the predicted wave field. This will lead to the considerably enhanced safety and efficiency in the marine engineering. However, in spite of the development, we are still not on a satisfactory stage for the wave prediction, especially because of the lack of the capability for the phase resolved wave modeling. And in recent years, there are still many accidents reported in the extreme wave state, in the extreme sea states. So to understand this problem better, it is worthwhile to provide a review of the state of the art for wave modeling. In general, there are two types of wave models, the phase averaged and phase resolved models. The phase averaged model is usually used in the large-scale prediction, for example, with a spatial scale from the order of 100 kilometers to the global scale. And the prediction horizon is pretty large in the order of days. And these models are relatively robust, and they have been applied routinely in the operational forecast to predict the sea states of the ocean. However, this model cannot serve the purpose of our current project because of the phase average property. So in other words, only the statistical information of the wave field is available, for example, the significant wave height or the peak wave period. And in other words, all the individual wave information is lost. For example, we cannot capture the individual rogue waves or marginally the individual dangerous waves. On the other hand, we have the phase resolved model, which can be used for the near field prediction with a spatial scale of about order of 3 kilometers. Depending on the equations solved in the phase resolved model, we can further classify this into the linear model and the nonlinear model. In the linear model, we simply propagate each wave mode by its phase speed. So this model can be run very fast, but with the sacrifice of the accuracy and the realistic dynamics. For the nonlinear model, it solves the complete nonlinear wave equation, which captures the exact nonlinear wave interaction effect and also the current and wind effect in a parameterized way. And because of this, the nonlinear wave model yields a much longer prediction horizon compared to the linear model. However, the problem for the nonlinear model is that the computation is usually very expensive, which requires CPU clusters, and that is not which is usually not available in the offshore environment. And also, the nonlinear models are usually developed and used for the physical study of ocean waves instead of the operational forecast. So it is not reliable to directly apply the nonlinear model in a realistic ocean environment because of the uncertainties involved in the computation. In general, the uncertainties can come from different aspects. So it can come from the initial conditions at the rate measurement of the ocean surface, which involves error. And also it can come from the uncertain wind and the current information in the ocean. In our project, our objective is to develop the real-time phase resolved nonlinear wave forecast. We need two key features of this new model. One is that we need it to be fast because we need a real-time forecast. And for that purpose, our solution is to accelerate the code on the GPU architecture, which can be conveniently installed on ships and ocean offshore platforms. Second, we need a new model to be reliable, and the solution is to use data assimilation to reduce uncertainty involved in the computation. We believe that this new capability will open a new paradigm in marine engineering. For example, here is one of the envisaged application in the autonomous ship path planning. We start with a rate measurement on the ocean surface to get a snapshot of the wave field. And then we put the snapshot into the CPU-GPU heterogeneous computation architecture, which will give us the prediction of the wave field in the next few minutes. And then according to this predicted wave information, we can conduct the optimal path planning, which gives us an optimal path for the ship that can either minimize the time or the energy or the risk. Then we can repeat this procedure so that we will end up with a continuous and sustainable autonomous path planning algorithm. The development of this research consists of two routes. The first route is on the data assimilation scheme, and the second route on the CPU-GPU code development. So eventually, these two routes will be merged, leading to the onboard applications. And in our MACD proposal, we propose to finish everything in the boxes in this 1 year period. Right now, we are working on the 3D scheme and wind current estimation, as well as the 3D GPU code development. We have finished everything for the 2D scheme, the validation and the code development, which will be the focus of our today's presentation. So from here, I'm going to hand over to my postdoc, Guangyao Wang.
Can you hear me now?
Yeah.
Yeah, we can.
Okay.
Yeah.
Let's move forward. So I will basically introduce the methods and the scheme and the results in the data assimilation framework. So let me first introduce the nonlinear wave model we used. The model we use is called high-order spectral method. There are two basic nonlinear wave equations which are corresponding to the kinematic and dynamic boundary conditions on the free surface. In the equation, the eta denotes the surface elevation, and the phi denotes the velocity potential, and we use psi x to represent the potential on the free surface. And phi z, which is equal to partial phi partial z, represents the vertical velocity of the free surface. If we look at the two equations, if we are able to evaluate the right side of the both equations, we can easily do the forward integration to get the solutions at any time point. However, if usually we only have the initial condition in hand. With the initial condition, we cannot evaluate the partial y, partial z. To address the issue, we need to look into the boundary value problem, which is shown below. The boundary value problem, in the boundary value problem, the computational domain includes both the free surface and the whole flow region under the free surface. The governing equation for the BVP problem is just a Laplace equation for the velocity potential, and we have the boundary condition on the free surface, which is phi x eta is equal to psi x. The psi x is given by the initial condition. By solving the BVP problem, we can get the partial phi and partial z, and then do the forward integration to get the solution of the wave field at all time points. In the HOS, we use a spectral solution for the BVP problem, and it is proved that this method is quite computationally efficient, and it has a quasi-linear computational complexity with respect to the nonlinear order and the number of modes. Okay, let's move to the next slide. The data assimilation method we used is ensemble Kalman filter. The basic idea of ensemble Kalman filter is to estimate the error statistics or cross matrix using an ensemble of model states. There are two basic steps in the EnKF. Let's look at the figure on right up figure on the right up figure. If we assume that we are starting from time tk, and we already have the analysis result at time tk in hand, which is denoted by EKA, then we can use the nonlinear model to move forward to time tk plus 1 to get the forecast result, which is denoted by EK plus 1f. With the model forecast at time tk plus 1, we can estimate the corresponding cross matrix at time tk plus 1, which is denoted by BK plus 1f. Now we have finished the forecast step. And the second step is called analysis step, which is to update the model forecast using the observations. In the context of the ocean wave, the measurement data are usually obtained with the onboard marine radar, which also has errors or uncertainties. The analysis result, EK plus 1A, is equal to the model forecast plus common gain times the difference between the observations and the model forecast. Here we have a new parameter which is called common gain. The common gain determines the relative weights of the measurements and the model forecast. It is a function of both the cross matrix of the forecast and the observations. Okay, let's move to the next slide. Okay, let me explain the EnKF and HOS coupled scheme. I have included all the equations just for the purpose of completeness. Let's just focus on the flowchart on the left side. In the simulation, we start with a set of noisy initial conditions, which includes both the surface elevation and velocity potential. Usually, the noisy initial conditions are obtained from the radar measurement. Then, based on the initial condition, measured initial conditions, we generate an ensemble of perturbed initial conditions just by adding a Gaussian noise to the measured initial conditions. Then, we run a bunch of HOS simulations on the ensemble of perturbed initial conditions until t equal to t plus tau. Here, tau denotes the data assimilation interval, and it depends on how often we can get the measurement data. And the last step is to incorporate the perturbed measurements into the model forecast to improve the accuracy of the solution, which is also called the analysis step. And we will repeat the last two steps until the end of the simulation. Okay, let's move to the next slide. Let's look at two example cases. The first one is an idealistic case in which we assume that the computer domain is finite and we can get the initial conditions for the whole computer domain. We first generate the exact solution, which will be used as a reference solution by running an HOS simulation running an HOS simulation without noise in the initial conditions, which means that we assume that the HOS methods has no model or noise. If the initial condition exact and the true solution and the solution exact, then we generate the noisy initial condition and the later measurements by adding a Gaussian noise to the true solution to generate the noisy measurements. The two figures below shows a comparison of the exact initial condition and the noisy initial condition. Okay, let's move to the next slide. Here, let's look at the result for the idealistic case. We first defined a normalized global error, error T, which is shown as the equation on the left upper corner. Then let's look at the figure on the left side. The figure shows the comparison of errors obtained with and without data and without data assimilation. If we do not do the data assimilation, which is shown as the right curve, the error induced by the initial noise will keep increasing. However, if we turn on the data representation, which is shown as the black curve, the global error will keep reducing as the time goes on. Although the error may experience high-frequency oscillations. And the right figure shows a comparison of snapshots of the wave field at t equal to 80 periods. The black curve is corresponding to the true solution, and the black dashed line is corresponding to the solution with data assimilation, and the red dashed line is corresponding to that obtained without data assimilation. It is quite clear that if we do the data assimilation, the solution, the result is more closer to the true solution than that obtained without data assimilation. Okay, let's move to the next slide. Then we conduct a parameter study to investigate the effects of data assimilation parameters. We first look into the impact of the number of assimilation locations. We consider 1, 2, and 3 assimilation locations. It is quite clear that as we increase the number of assimilation locations, we can reduce the global error as well, and we can improve the error reduction rate. Then we look into the impact of data assimilation interval tau. It shows that as we decrease the data assimilation interval, we can improve the error reduction rate and the magnitude of the global error. Finally, we look into the size of ensemble, which means that how many members we have in the ensemble. When we have only 10 members in the ensemble, the global error first increases significantly and then approaches a constant. The main reason is that with 10 is too small to provide a very accurate estimation of the current matrix, which will lead to the increase of the global error. However, if we increase it from 20 to 100, we can see that the global error will be reduced and the error reduction rate will be improved. So we can summarize that the performance of the EnKF and HYS couple scheme could be improved by increasing the number of assimilation locations, reducing the assimilation interval, and increasing the size of the ensemble. Okay, let's move to the next slide. Then we look into a more practical case, because if we want to simulate the wave in the real ocean environment, the computing domain should be infinite instead of finite. So in that case, we may able to only get the information for one part of the whole domain. For example, let's look at the figure on the left side. At t equal to 0, we may only be able to get about 1/4, or we may only be able to get the information for the first quarter of the computer domain, which may be limited by the which is mainly determined by the radar parameters. As the wave is traveling to the right side, we can see that the predictable zone is shrinking. The main reason is that the range or the length of the predictable zone is mainly impacted by the wave group velocity CG. The wave group velocity determines the rate of how fast the wave information or wave energy is transported by the wave. And the right end of the predictable zone is determined by the minimum value of the group velocity, while the left end or the back end is determined by the max value of the group velocity. So as time goes on, the predictable zone will shrink and finally collapse. In study, we only use 2 assimilation locations. and the two assimilation locations are always within the predictable zone when we are performing the simulation. Let's look at the figure on the right side. With only two assimilation locations, we can see that the error obtained with data assimilation is still much smaller than that obtained without a data assimilation scheme.
Okay, so both HOS and EnKF are intrinsically parallel. So to understand how we might best optimize our GPU code for this application, we have to understand first the CPU-GPU heterogeneous architecture. We see here we have two different systems. One, the host, which has some relatively small number of CPUs that are each low latency and good for low volume parallel computation. On the other hand, we have the GPU, which has a high number of compute units, each higher latency, but is good for high volume parallel computation. The GPU also has a hierarchical memory structure in which each thread running on the GPU has access to global memory, which is the slowest of the three. Clusters of threads each have their own shared memory, which is considerably faster than global memory. And not depicted in the diagram is local memory, which is specific to each individual thread, and that's the fastest of all. So to optimize our GPU acceleration, we need to minimize the time the GPU waits for work so that it's always doing something. We need to minimize the CPU to GPU data transfers as they are slow. And we need to maximize the use of GPU shared and local memory as those are faster than global memory. This amounts to keeping all of our large arrays on the GPU for as long as possible and doing all of our array operations and FFTs in parallel in that environment. The CPU, on the other hand, takes care of the control sequences as it's low latency and tells the GPU what to do and handles the I/O when the time comes to take the data off of the device. The next slide. So we've implemented our system in CUDA Fortran, and we have some performance benchmarks to test the accuracy and speed of our code. First, we test the accuracy of the boundary value problem solution. We run a Stokes wave case in which we analytically know the surface vertical velocity profile that we are approximating in HOS. When we increment the nonlinear order M and check the error, we find we have exponential convergence to the true solution for a variety of nonlinear strengths. That's, in this case, wave steepness, just as predicted by the theory. We then compare the performance of our CPU-GPU code to serial CPU code for a variety of numbers of modes in our simulation. And we find that as we increase the number of modes, we achieve better and better performance relative to the serial CPU code, up to 2 orders of magnitude increase in speed for 2 to the 16 modes. The black line in the middle plot is the real-time limit, which is estimated by a 1 kilometer patch of wave field with the same number of modes as the x-axis of the plot. And we see that we are much faster than real-time, even to a large number of computational modes. Lastly, on the right-hand side, we compare real-time to runtime as real-time divided by runtime for varying numbers of ensemble members at 2 to the 14 modes. We choose 2 to the 14 because it represents a 128 by 128 grid, which is great for a realistic computational domain. And we find that while we far exceed real-time performance for one member of the ensemble, we maintain roughly 30 times speed relative to real-time, even in the case of 128 members, which is plenty fast for real-time application.
I'll just jump in here to say there's about 8 minutes to the end of the presentation, to about 30. So you have about 3 or 4 minutes to finish up, and then a few minutes of questions.
Yeah. Yes. So,
that's all.
Yeah, so there are still some room for the improvement for the GPU performance in terms of speed, but we consider that the 2D code and the algorithm are pretty much done. For the future work, we will work on the 3D scheme development that includes wind and current parameter estimation, as well as the 3D GPU code development. And after that, we will validate our method using the real data that is provided by a previous ONR project led by our department. And we also plan to couple with a planning task planning algorithm, which is also under development, and finally is onboard implementation. For the publication and funding, we have one paper published on the part of the 2D data simulation scheme, and we have two planned, one for the 3D scheme and one for the GPU computation. For the funding application, I have one proposal under review for the C-train program in DARPA. So this project aims to develop the connected vessel in the ocean like a train, and the purpose is to reduce the drag and increase the efficiency of the transport. The key issue in this project is to develop the wave prediction algorithm, real-time wave prediction capability so that the control of the C-train can be implemented in real time. And this whole project is led by GE, and in the first phase, the total funding is 10 million, and we have 1.8 million for So this will be used for the hydrodynamic optimization, towing tank experiment, and wave prediction. So if we get this, then we'll have sufficient funding for further development of this project. And if not, we still have two alternative choices for ONR and NSF. And finally, I would like to thank Mike D for supporting this project. In fact, this is something that I envisioned during my PhD period. So it is a great pleasure to be able to work on this finally. And also, I would like to thank our department for the support in research, especially Professor Bob Beck and Dave Lazinger for providing the radar data to support this research. So I will stop here and thank you very much, and I'm ready for questions.
Thanks very much. Thanks, Yulin. Thanks also to Guang Yao and Alexander. Maybe as before, I can start out with the question, and maybe others will show up in the chat box. So one thing it's not immediately clear to me is that as you're assimilating data, what parameters or maybe fields in your computation are you updating? Because I guess you're doing data assimilation, so I guess you either have some priors for parameters and you're updating those, or maybe the solution itself is what you're updating to as you're correcting.
Yeah, so basically the radar will provide a measurement of the surface elevation, which is the parameter eta in the equation. So in our forecast step, we will get the eta as a function of t at that particular time instant where the radar data comes in. So in the data simulation, we update t according to the Kalman gain equation, and then we also update psi using a sort of estimation of also from the radar. So basically, the radar provides the solution of eta and an estimation of solution of psi. I mean.
I see. And in real applications, the data assimilation rate is high enough. I don't know whether you use synthetic data in this, or was these real data that?
So the radar can be used every maybe 10 seconds or 20 seconds to scan the ocean surface.
I see.
Yeah.
Okay. Any other questions?
There are no questions in the chat.
Okay. So what are there other approaches being taken broadly in the field to get to real-time forecasting?
So right now the method used is mostly the linear model for the phase result forecast. So the nonlinear model is developed, but they are mainly used for the physical study of the waves, not for the operational forecast. And so the reason is that these uncertainties, and also it is too slow. So for the data simulation part, there is some research on using the variational method for the data simulation, but we think for the operational forecast is more it is more suitable for using the Kalman filter type of method to do it.
So I see that there is a question from the attendees. Alexander Gainko asks that when comparing CPU and GPU performance, was the CPU single or multi-core? The CPU, was it single core or multi-core?
Maybe Alex knows the details of the CPU.
Yes, it was a single core program.
Okay. Sorry. Clarification. Oh, sorry. Single or multi-thread CPU computation. I guess you said single core program, but was it single or multi-threaded?
Single-threaded CPU computation.
Okay. I see. And you said single core as well? Single thread on a single core?
Yes.
Okay.
Yes.
Okay. Okay. I don't see any other questions right now. So if there aren't any...
Oh, no. Nothing came up. Sorry.
Nothing? Okay. Okay. Yeah. No, so thanks again. Thanks to Yulin, Guangyao, and Alexander, also to Robert and Vikram. So also thanks to everybody for accommodating this very different format. I think it worked okay. Of course, this thing never replaces an actual seminar, but we do as well as we can. Hopefully, this is beginning to give you some sense of the different projects that have been part of the Catalyst Grant program. You will see quite a different set of projects in the afternoon session, which begins at 1. There we have Steve Smith from Ecology and Evolutionary Biology, Xuan Han from Mechanical Engineering, and Monica Valuri from Astronomy, presenting their work. And as you can imagine, just from those departments, there's quite a range of different types of science, computational science, that we will be talking about then. So if there are no other questions, we can thank everybody and hope to encounter all of you again at 1 o'clock. Thanks.
And just a quick note that it's a different link for the afternoon session. It's not the same link. And it's on all our pages and information.
Okay, great.
Yep. Thank you, everyone.
Thanks, everyone.
Thank you, Krishna. Thank you, Mariana.
Yeah, thanks, everyone.